Welcome to the deep dive. Today we are doing exactly what the name says, a deep dive into a really foundational piece of the internet.
Yeah, you shared RFC 792 with us, which goes way back to September 1981.
1981. And it details the Internet Control Message Protocol, ICMP.
And this one's absolutely crucial. The RFC itself calls it an internet standard, an integral part of IP. Looking at these early specs is, well, vital for understanding how things work even today.
Right, going back to the roots. Okay, so our mission today is to really unpack this ICMP thing, pull out the key ideas from this original document. So let's start right at the beginning. What is ICMP? And why does IP, which is for, host-to-host datagram service, why does it even need it?
Okay, so think of IP, the Internet Protocol, as like the basic postal service for the Internet.
Yeah.
It takes these packets, or datagrams, as the RFC calls them, and it tries its best to get them from A to B.
Tries its best.
Yeah, exactly. The RFC is super clear. IP is not designed to be absolutely reliable. It's best effort. No guarantees it gets there, or in what order. And crucially, it doesn't automatically tell the sender if something went wrong.
Ah, okay. So like dropping a letter in the mail, you hope for the best, but no tracking, no return to sender built in.
Precisely. And that's where ICMP steps in. The RFC says it's used by gateways, think routers, and the actual destination hosts to talk back to the original source host.
To talk back. About what?
Mainly to report an error in datagram processing. It's the mechanism for the network or the destination to say, hey, that packet you sent, yeah, there was a problem.
Got it. So IP sends, ICMP reports back on the send. Now, the RFC says something interesting, that ICMP uses the basic support of IP as if it were a higher level protocol.
Yeah.
But it's actually an integral part of IP. What's the deal with calling it integral?
That's a really key point. It means ICMP isn't just another application using IP, like, say, web traffic using TCP over IP. It's built into the IP layer itself.
Okay.
Every device that handles IP is required to understand and process the ICMP messages that relate to basic IP functioning. It's not optional. It's part of the core IP specification.
But you said its purpose is just feedback, right? To provide feedback about problems, not to actually make IP reliable.
Exactly. The RFC stresses that. If you need reliability, making sure packets arrive in order and are acknowledged, that's the job of higher level protocols. Think TCP. ICMP is purely informational diagnostic. It tells you about the network's state, not fixing the packet itself.
Okay. So what kinds of problems trigger these ICMP messages, according to the source?
Well, the RFC lists a few key ones. Obviously, if a datagram just cannot reach its destination, that's a big one.
Makes sense.
Also, if a gateway, a router, lacks buffering capacity, basically it's getting swamped with too much traffic and has to drop packets.
Congestion notification, kind of?
Sort of, yeah. And interestingly, it also mentions if a gateway can direct hosts to a shorter route. So it's not just errors, but also potential optimizations.
Errors, congestion, and routing hints. It covers a bit of ground.
It does. But the RFC also points out some really important limitations. You need to remember these.
Okay, like what?
First, there's no guarantee a datagram or control message will be delivered. So even the ICMP message telling you about an error might get lost itself.
Oh, great. So you might not even know something went wrong.
It's possible. Which leads directly to the second big limitation, maybe the most famous one. To avoid the infinite regress of messages about messages, etc., no ICMP messages are sent about ICMP messages.
Right. If an ICMP error message has a problem, you don't get another ICMP message about that problem. Stops the feedback loop from spiraling.
Exactly. Smart design. And one more subtle point. ICMP error messages are generally only sent about errors in handling fragment 0 of fragmented datagrams.
Fragment 0, what does that mean?
If you have a big chunk of data, IP might break it into smaller pieces called fragments to send it. Fragment 0 is the first piece. If an error happens with one of the later pieces, you might not get an ICMP message back about it. The focus is on errors related to that first fragment.
Okay, interesting nuance. So we get the why and the what. What about the how? How are these messages actually structured? What do they look like?
Right, the format. ICMP doesn't get its own fancy header at the IP level. It actually travels inside the data portion, the payload, of a standard IP packet.
Oh, okay. So it piggybacks on IP.
It does. And the RFC says the very first byte of that data payload is the ICMP type field. That one byte tells you everything. Its value determines what kind of message it is like. Is it an error? Is it a request? Is it a reply? And that then defines how the rest of the message is formatted.
Got it. So IP packet arrives, Look at the IP header, see the protocol field says ICMP, which is protocol number 1. Then you look at the first byte of the data part, and that tells you what kind of ICMP message you've got.
Exactly. And after that type field, there are usually a few other common fields. There's the code field. This gives you more detail within a specific type.
Like a subtype.
Yeah, kind of. For example, type 3 is destination unreachable. But the code field tells you why. Code 0 might mean the network is unreachable, code 1 the host, code 3, maybe the specific port isn't open on the destination machine.
So type is the category, code is the specific reason. Makes sense.
Then there's a checksum. It's a 16-bit field used to check for errors in the ICMP message itself. The RFC specifies the calculation method 1's complement sum, calculated with the checksum field initially set to 0.
Standard error checking.
Right. There might also be unused fields reserved for the future. The RFC says these must be 0 when sent. And critically, for many error messages, it includes the internet header plus 64 bits of original datagram.
Okay, wait. It includes part of the original packet that caused the problem. Why?
That's the context. By sending back the IP header and the first 8 bytes or 64 bits of the data from the original packet, the source machine can figure out which of its communications caused the error.
Because those first few bytes might contain, say, the TCP or UDP port numbers.
Exactly. That helps match the error back to the specific application or process that sent the packet in the first place. It's like getting a returned letter with a copy of the first line you wrote so you know which letter bounced.
Okay, that's clever. Really helps with diagnostics.
Definitely. And remember, all this is inside an IP packet, so you still have the standard IP header stuff. IP version 4, protocol field set to 1 for ICMP, the source address who sent the ICMP message, and the destination address who it's for the original sender.
All right, I think I've got the general idea. Let's make this more concrete. Let's dig into the specific message types described in this RFC. What kind of feedback were they defining back in 81?
Okay, yeah, let's get into the specifics. The RFC lays out quite a few. Probably the most common error you'll encounter is destination unreachable. That's type 3. Like we touched on, the code tells you why. Code 0, network unreachable. Code 1, host unreachable. Code 2, protocol unreachable. Maybe you tried to use a protocol the destination doesn't support. Code 3, port unreachable. The host is there, but the specific application port isn't listening.
Okay, those seem pretty clear.
The RFC notes, which usually come from a gateway, like code 0, 1, 4, 5, versus the final host codes 2, 3. And code 4 is interesting.
Remind me, that was the fragmentation one.
Right. Code 4. Fragmentation needed and don't fragment was set. Your packet was too big for a part of the network path, but you told the network, do not fragment this packet. So the gateway had to drop it. It might send back this type 3 code 4 message. This is directly tied to path MTU discovery issues people sometimes run into.
MTU, maximum transmission unit. Got it. And like other errors, it includes the original header and data snippet.
Yep. Original IP header plus 64 bits of data. Essential context.
Okay, so that covers various can't get there scenarios. What about things related to time or the path itself?
That brings us to time exceeded, which is type 11. This usually signals that a packet was looping or just took too long to get somewhere. Code 0 is the classic one. It's sent by a gateway, a router, when the time to love field, the TTL in the IP header counts down to 0.
The TTL, that's the hop counter, right? Prevents packets wandering forever.
Exactly. Each router is supposed to decrement it. If it hits 0, the router must discard the packet and should send back a time-exceeded code 0 message to the source.
And this is the magic behind Traceroute.
Absolutely. Traceroute tools cleverly manipulate the TTL, sending packets with TTL 1, then 2, then 3, and so on. Each router that drops the packet, because TTL hit 0, sends back a time-exceeded message. That's how you map the hops.
Wow. So Traceroute is basically built on this 1981 ICMP message.
Pretty much. There's also code 1 for time exceeded. This comes from a host if it's trying to reassemble a fragmented packet but doesn't receive all the pieces within its time limit. It gives up, discards what it has, and might send back a type 11, code 1. Again, includes the original header plus 64 bits.
Okay. What if the problem isn't the path or time, but the packet header itself is just wrong?
That's parameter problem type 12. Sent by a gateway or a host if it finds something messed up in the IP header fields that prevents it from processing the packet, maybe an invalid option or just bad formatting. The packet must be discarded.
And does it say what was wrong?
Yes. If the code is 0, it includes a special pointer field. This pointer is a byte offset. It points to the exact byte within the original IP header where the error was detected.
Seriously, it tells you the byte number.
Yep. The RFC gives examples. A pointer value of 1 means the error is in the type of service byte. 20 means it's in the first byte of the first IP option. It's incredibly specific for debugging header issues. And yes, includes the original header plus 64 bits.
That's impressive detail for 81. Really helps pinpoint header formation bugs.
Definitely. Now, moving towards network conditions, there's source quench, type 4.
Quench, like telling the source to cool it.
Exactly. This is sent by a gateway or host that's getting overwhelmed. It's discarding datagrams because it's out of buffer space or they're just arriving too fast. The source quench message is basically a request, hey, source host, please slow down sending packets to this destination.
A kind of basic congestion signal?
A very early form, yes. The RFC says a gateway might send one for every packet it drops due to congestion, or maybe just when it's getting close to full. The idea was the source host should then reduce its sending rate and slowly ramp back up.
Does this still get used much? I thought TCP handled most congestion control now.
You're right. TCP's sophisticated algorithms are the main way congestion is managed today. Source quench is, let's say, less relied upon now, but it's in the spec. It also includes the original header plus 64 bits.
Okay. What about that routing hint you mentioned earlier?
Right, that's redirect type 5. This one's interesting. It's sent by a gateway, let's call it G1, but only to a host that's on the same local network as G1.
Okay, so my router talking to my laptop, for instance.
Yes. It happens if your laptop sends a packet to G1, aiming for some destination network X, but G1 looks at its routing table and realizes that the best next hop router to reach network X, let's call that G2, is also on your same local network.
Huh. So my router knows there's another router on my network that's a better path.
Exactly. G1 sees that you could have sent the packet directly to G2 instead of sending it via G1 first. So G1 forwards your original packet, but it also sends your laptop a redirect message. This message basically says, hey, for future packets to network X, send them straight to G2's IP address instead of me.
It's teaching my laptop a better route for that specific destination.
Precisely. It's an efficiency thing. The message includes the IP address of the better gateway, G2. There are different codes depending on whether the redirect is for a whole network, a specific host, or based on type of service, too. It's not sent if the original packet used source routing options, though.
Clever. Dynamically updating the host's view of the local network topology.
Yep. Okay, now for the real diagnostic workhorses, the ones people probably know best, even if they don't know the names. Echo or echo reply, type 8 and type 0. That's the one. Echo request is type 8. You send it to a machine to see if it's alive and how long it takes to respond. The sender includes 2 fields, an identifier and a sequence number.
What are those for?
Just ways to keep track. The identifier might be unique to the ping process you started, and the sequence number usually increments for each ping you send. This helps you match the replies back to the specific requests you sent, especially if you're pinging fast from multiple places.
Okay, makes sense.
The machine that receives the echo request, type 8, is supposed to respond with an echo reply, type 0. It flips the source and destination IP addresses, changes the type to 0, keeps the same identifier and sequence number, and, this is important, it must include any data that was sent in the original echo request.
So whatever data you put in the ping packet should come back in the reply.
Exactly. Ping tools often let you specify the size of this data payload. And the time between sending the request and getting the reply, that's your round-trip time. Basic, fundamental network testing, all built on ICMP types 8 and 0.
Amazing how fundamental that is. Still used constantly.
Absolutely. Then, similar but different is timestamp or timestamp reply types 13 and 14.
Okay. Sounds like it involves time.
It does. Also used for measuring round-trip time, but potentially also for getting a rough idea of clock synchronization, though that's less common now. Like Echo, the timestamp request type 13 includes an identifier and sequence number for matching. The timestamp reply, type 14, comes back with reversed addresses. Type 14, same identifier and sequence number. But instead of just data, it includes 3 32-bit timestamps.
3. What are they?
There's the originate timestamp, when the sender last touched the request before sending, the receive timestamp, when the receiver first got the request, and the transmit timestamp, when the receiver last touched the reply before sending it back.
Whoa. So you can see not just the round trip, but potentially how long it spent on the wire each way and how long the other machine took to process it?
That's the idea. It gives a more granular view of the timing. The RFC specifies these are milliseconds since midnight UT-coordinated universal time, though a flag could indicate non-standard time.
Again, really detailed diagnostics for 1981.
They were thinking ahead. Okay, one last pair from the RFC. Information request or information reply types 15 and 16.
Information request. What kind of information?
The RFC describes it mainly as a way for a host to find out the number of the network it is on. A host could send an information request, type 15, maybe even with its own network address field set to 0, meaning this network.
Kind of like asking, where am I?
Sort of, yeah. A gateway or another IP module receiving it was supposed to send back an information reply, type 16, with the correct, fully specified network and host addresses filled in. Like echo and timestamp, it uses an identifier and sequence number for matching.
Huh. Is that still used? Seems like DHCP handles that now.
Right. DHCP is the standard way hosts get their network configuration today. This ICMP method is more of a historical footnote, but it shows they were thinking about how devices could discover their network context early on.
Okay, wow. So looking back at all these, destination unreachable, time exceeded, parameter, problem for errors, source quench for congestion, redirect for routing hints, echo and timestamp for direct diagnostics, and even information request. It's a pretty complete toolkit for basic network feedback, defined way back then.
It really is.
And here's where it gets really interesting for me. How these seemingly simple, low-level messages, form the foundation for tools we still absolutely rely on every day for troubleshooting.
Exactly. That's why looking at this 1981 RFC isn't just like an academic exercise. It's still incredibly relevant. These messages are how devices signal status, report errors, check connectivity. They're the bedrock of network diagnostics.
Yeah, you've probably used ICMP dozens, maybe hundreds of times without even realizing it was ICMP. Every time you run ping, that's echo, request, and reply.
Right.
Every time you run traceroute or traceroute, you're seeing time-exceeded messages, maybe a destination unreachable at the end. It's all powered by these message types we just walked through, defined in RFC 792.
And understanding them, even at this level, helps you make sense of what those tools are telling you. You see that ping output or that traceroute hop, and now you know the specific conversation that's happening underneath using these ICMP messages. It shows that layered design of the internet in action.
It really demystifies it a bit. Okay, this has been a fantastic deep dive. Seriously, thanks for sharing the source material with us. It led to a really insightful look at a core protocol.
Absolutely, and it really highlights the value of sometimes going back to these original documents, the RFCs. You get a much clearer picture of the fundamental concepts and the why behind how things work.
Couldn't agree more. All right, let's leave you, our listener, with a final thought to chew on. Given everything we've discussed, especially, that ICMP is explicitly not designed to make IP reliable, and even the ICMP messages themselves aren't guaranteed to arrive. How does this whole system, built on these fundamentally unreliable pieces, manage to create the incredibly complex and largely reliable internet that we depend on every single day? Something to think about.